So I'm going to teach you guys about how chemical reactions occur in cells with the help of enzymes. So we're going to do the chemical reaction of hydrogen peroxide breaking down. So 2H2O2 is going to go to two products, water and oxygen gas. Okay, so we're going to make 2 waters and 1 oxygen gas. Alright, so in order to do that, we're going to use an enzyme called peroxidase, which I'm just going to use as my hands. Okay, so in this energy diagram, this is the free energy, or G, and this is time, or the progress of the reaction. So the free energy is the energy stored in the bonds of the molecules that we have. So right now we have the reactants, which is the hydrogen peroxide. And then we're going to have the products when we're done, which will be the water and oxygen. And so you can see there's less energy in the free energy in the products than in the reaction, and then in the reactants. So this is going to be an exergonic reaction because we'll have less energy in the products than in the reactants, so it's going to release energy. Another way of saying this is that the delta G is less than 0 because the delta G is the change in G, so that's the free energy of the products, which is a smaller number, minus the free energy of the reactants, which is a larger number, which will be less than 0. So exergonic reactions have a negative free energy. Okay, so they're going to be spontaneous, but we've got this energy of activation. That's the amount of energy that it takes to get from the reactants to getting the reaction going. So that's the energy of activation, or EA. And what an enzyme is going to do is it's going to lower that energy of activation. That's because what the enzyme is going to be doing is it's going to strain, it's going to put the reactants in its active site and it's going to strain the bond. So it's going to position the reactant in such a way that the reaction can occur really easily. So this bond is going to be strained such that it'll break. A model that I use a lot to show this is this color-changing ball. So the color-changing ball can go from being blue to being purple. So you can think of blue as being the reactants and purple as being the products. But to get from the reactants to the products, you have this really unstable intermediate, which is called a transition state. And on this diagram, this is the transition state here. And that's that high energy intermediate. You see it's the highest energy of all of them. And that's this like almost not quite products, not quite reactants. It's this really unstable high energy intermediate form. So what the enzyme does when it puts the reactant in the substrate, the reactant in the active site, is it positions the substrate such that it's really stable in the transition state so the reaction can occur quickly. So the enzyme again positions the reactant and kind of tugs on the bonds so that the transition state is stabilized. So instead of the transition state having this high energy, the transition state is going to have a lower energy with the enzyme. So this is with the enzyme. It lowers the energy of the transition state, so it lowers the amount of energy that is needed for the reaction. So now if you have an enzyme, the reaction can occur more quickly. So hydrogen peroxide, if you've seen the bottle of hydrogen peroxide that you might have at your home, it's in a dark bottle because spontaneously hydrogen peroxide will break. And when it breaks, it forms water. So here we have water, 2 waters. And then what you have left is oxygen gas, which we're going to need to connect the double bond here. So there's our products. So that'll happen spontaneously in a bottle of hydrogen peroxide if you allow it to be exposed to light. So eventually all your hydrogen peroxide will turn into water and oxygen. The oxygen gas will escape, and all you'll have is water, which won't work very well as an antiseptic. So that's why they put it in a dark bottle. But if you had the enzyme peroxidase, that reaction would happen in seconds. And that's because the enzyme would bring that reactant to the transition state so that it would happen much more quickly. In fact, the enzyme peroxidase is one of the fastest enzymes on Earth. It can do millions of reactions per second. So it can bring the reactants quickly to the transition state so that they can become products. So that would be an exergonic reaction. In order to do an endergonic reaction, so in other words, if like we wanted to turn water and oxygen into hydrogen peroxide, we're going to need energy to do that. A lot of energy. And generally when you're doing that, you're doing anabolism, which is going to require ATP. So to do a reaction that is endergonic, in other words, anabolism, where the reactants have a lower free energy than the products, we're going to need to provide energy in living cells that is provided by ATP. So the reactants are generally phosphorylated. So the phosphate group usually attaches to the reactants. That brings the energy of the reactants way up. And then the enzyme, because you can still lower this transition state with the enzyme. And so both ATP and the enzyme you can get from the reactants to the products. So this would be an endergonic reaction. Or, same thing, would be anabolism. And in this case, you'd need ATP and the enzyme. Whereas with an exergonic reaction, all you need is the enzyme.